This Java file looks simple, but a full platform hides behind it. Most learners first see Java as syntax, classes, and semicolons only. Behind that file, the compiler waits to check and transform code. After compiling, Java becomes bytecode, not a normal native executable file. Then a platform-specific JVM runs that bytecode on the machine locally. Around this runtime, tools and frameworks turn Java into production software. So remember the formula: language, compiler, bytecode, JVM, and ecosystem together. The pipeline starts with source code, the file developers actually write. Now Javac appears as the bridge from source to runtime-ready output. The output is a .class file, which contains portable bytecode instructions. That same bytecode can move toward different operating system JVM safely. The Windows JVM understands bytecode and runs it for Windows machines. The Mac OS and Linux JVMs understand the same bytecode too there. Each JVM finally produces behavior the local machine can execute safely. The key correction is simple: bytecode travels, JVMs are platform-specific runtimes. This pipeline is the foundation for every Java application built later. Now we zoom into the first layer, the Java source file. This layer is the code humans read, write, and review. Java asks you to be clear about the types involved. It also organizes code around classes, objects, state, and behavior. The language hides many machine details, so developers focus on logic. At this stage, we are not writing direct CPU instructions. The source file captures developer intent before any conversion happens. Once the source exists, Java needs a compiler to transform it. The next layer is Javac, Java's source code compiler tool. The .java file moves into Javac before any bytecode appears. First, Javac checks whether the source code shape is valid. Then it checks whether values and types are used correctly. It also checks the class structure before producing compiler output. A simple command anchor is Javac followed by the file name. The output is myClass.class, a bytecode file for the JVM. This is the trap. Javac does not create a native executable. Now the important question becomes, what exactly is inside .class? Here the .class file represents bytecode, Java's portable instruction format. It is not source code anymore but not CPU code either. Think of bytecode as a package that JVMs know to open. The same bytecode can move toward a Windows machine. It can also move toward a Mac OS machine unchanged. And it can move toward Linux with the same bytecode. The file stays the same, the runtime changes around it. That is the practical idea behind write once, run anywhere. But bytecode still cannot run alone. It needs a JVM. So next, the portable file meets the platform-specific JVM. Now 3 JVM boxes appear, one for each operating system. The same .class file can enter the Windows JVM. The same .class file can enter the Mac OS JVM. The same .class file can enter the Linux JVM. The bytecode is portable, but each JVM is platform-specific. Each JVM translates execution into behavior for its local machine. So the JVM is the runtime engine that runs bytecode. The common trap is saying the JVM itself is platform independent. The correct memory is portable bytecode, platform-specific JVM. Now we open one JVM box and only inspect the big helpers. These helpers explain how the JVM supports execution at runtime. Inside the JVM, keep the map simple and high level. The ClassLoader brings needed .class files into the runtime. Memory management gives objects space while the program is running. The garbage collector reclaims memory from objects no longer used. The interpreter can start running bytecode without waiting for optimization. The JIT compiler improves code paths that run again and again. When code becomes hot, JIT can compile it into native code. Together, these help us load, manage, run, and optimize Java code. For this first mental map, we do not go deeper yet. The JVM is the execution engine, plus these runtime services. Now we zoom out from the engine to the Java ecosystem. The next map shows how runtime and developer tools fit together. Start with the JVM at the center of the ecosystem. The JRE wraps the JVM with libraries needed for running. The JDK adds developer tools on top of the runtime. That is where Javac belongs, a development tool inside JDK. Tools like jar, JDB and Javap also support development. Runtime libraries provide common APIs programs need while running. OpenJDK is the open source foundation behind Java distributions. Maven and Gradle help build, package, and manage projects. Spring Boot sits above core Java for backend application development. Keep the distinction simple. JVM runs, JRE supports, JDK builds. Now all pieces collapse into one final Java mental map. The final map starts with Java as the center idea. The language branch is where humans write .java source code. The compiler branch is Java checking and converting source. The Bytecode branch is the portable .class output format. The JVM branch is the platform-specific runtime that executes bytecode. The ecosystem branch contains tools, libraries, frameworks, and distributions. The strongest memory line is source, compiler, bytecode, then JVM.